Okay, hello everyone. Hope you all have had a good day. So we are just going to continue. We're just going to continue what we have left in the morning. So today we have started learning channel modeling, and in the morning, let's recap first. In the morning, we from this slide, we looked at two definitions of bandwidth. So first is system bandwidth. Second is the coherent bandwidth of the wireless channels. So when signal bandwidth is smaller than the channel bandwidth, the signal can go through the channel without any harm. For the rest, things get a little bit complicated. We need OFDM to divide the signal bandwidth into sub-channels. So this is the one I told you in the morning that I want you to take a mental picture of this slide. So in the following 2 or 3 sessions, we'll be focusing on this channel modeling. There are 3 levels of channel modeling. The first level is propagation path loss, which is power loss over distance. Second is the shadowing effect, which is a power blockage caused by buildings or hills or any obstacles. The third is small-scale fast fading, which not only cause amplitude change, but also cause phase change. So for the first 2 levels of fading or path loss, we are mainly dealing with power loss of the received signal. And then for the small scale fading, because we need to compensate. So for the first 2 levels, we need to know those blockage and we need to know those path loss. Those are power loss in a very large scale. So we need to know them beforehand. As a transmitter, we will increase the transmit power in order to compensate for that power loss. But fast fading is another story. It is fading in a smaller scale. On average, the power is 1. So sometimes it's better, sometimes it's worse. And also because signals, they are added together as a transmitter with different delays and different phase shifts. So small scale fading would also take into account the phase shifts. So we will consider complex value signal later. So this is what we'll talk about later today. So remember, this is 3 levels of channel modeling, and for each level, there are different methods as well. Different methods, they are suitable for different scenarios. So in the morning, we talked about propagation path loss, and we introduced 3 types of propagation path loss. The first one, let's just skip this one now. So the first one is free space path loss. Free space path loss, which is associated with a situation when there is only line of sight. So it's more suitable for satellite communications, or it can be used as a reference in general wireless communication scenarios. So we talked a lot about these equations. One correction I have to make for my morning explanation is that so when we talk about radiation, power radiation, we are only talking about the transmit power here. So this is a radiation power, and this is a power that is regulated by standard. So it is regulated by 5G standard, or 4G standard, or Wi-Fi standard. So this is a radiation power, which is also the transmit signal power. And then the antenna guns, they are fixed once manufactured. So they are not really signal powers. So in the morning, probably if you listen back my lecture, you probably hear me saying a lot of times that we need more power here as a antenna gun. But antenna gun is not power. It is when you have, for example, when you have a larger area, you can glean more signal power when you receive signal power. That's an example, but it doesn't cause radiation power. So that is a correction for my lecture in the morning. Anyway, all these parameters, we have learned the meanings of them in the morning, and the biggest takeaway is that the level of received signal power is a function of distance. So as the distance increases, the received signal power would reduce. So we further expand the equation to express it in decibel, so in dB, so that we can separate all those parameters. We can look at them separately. So that's motivation of expressing it in dB. And also, it is for the convenience of real-world engineering. And equivalently, we have this equivalent form, which is in different magnitude. So when you evaluate path loss, sometimes you only want to input distance in the magnitude of kilometer, or frequency in the magnitude of megahertz. So this is for the convenience of real-world engineering. So free space propagation is the first path loss. So the level 1 channel modeling. The second method for path loss is ground reflection model. We probably didn't say this. We probably didn't get here in the morning. So ground reflection model is a second path loss model. We can directly look at this figure. So this is a good example that if you can draw this figure on a piece of paper by yourself, you will be able to explain the definition of this ground reflection path loss model. It will help you to understand it as well. So you can see this model is, sometimes also called two-ray model, because you have a direct line of sight and you also have a reflected link. So in the morning, we mentioned that when base station is transmitting signal, the signal would go everywhere, and there will be a lot of reflections. However, for this model, the assumption is that from the mobile station's point of view, so as a receiver, it receives substantial power from two sources. So it understands the channel by building it in a two-ray model, because line of sight is always there. The other one is a reflected link. So it doesn't apply to every scenarios. So this scenario, for example, is more suitable for communication in rural area. When there is open space, there is no other hills or buildings that cause other reflections and any other effects. Um, and it's also more suitable for aeronautical communication when the airplane is transmitting signal to a base station, and there will be a reflected link from the ground. So for this, in order to model this model mathematically, we have to make some assumptions. The assumption we make in here is that the signal power of the direct line of sight equals to the signal power of the reflected link. However, in reality, normally the reflected link has smaller power, because normally the reflected, when the signal travels along a reflected link, the distance of this link is longer than this link, right? Because the shortest path is a direct link. So when signal travel over distance, it would fade over distance. So normally the reflected link has smaller power. But for the sake of mathematical modeling, for this model, we'll assume that both links, they have the same power. Another assumption is because of the reflection, there will be a phase change. So two links, they can either act constructively or destructively. It is more of a random effect. We have no control of this. So if we interpret that effect by equations, we arrive at equation 7, which is constituted by two parts. The first part is the same as before, which is the free space path loss. So it's only related to distance. The second part, the second part interprets the reflection and the direct link. So theta is the phase difference between the reflected signal and the direct line of sight signal. So as I said before, sometimes two signals, they would act constructively together, sometimes destructively. So if you look at this element here, when theta equals 0, sin pi over 2 is 1. And we have two links, so the parameter here is 2. Then the overall power for the received signal is actually enhanced. However, if theta equals pi, sin 0 is 0. So here for the received signal, we don't receive any power at all. So the two cases are both corner cases. They are not, we have no control over them. But that's how two signals adding together can give us a sense of randomness. But I said earlier, for the first here, this is still the first level of channel modeling, so path loss. For the first level of channel modeling, we only want to evaluate the signal power, not the phase. So if we look at the ground reflection model, we want to evaluate the received signal power, right? And when we evaluate this equation, one part that is particularly hard to evaluate is this one, because you need to estimate what theta is for each transmission model, for each scenarios. That's really hard to measure, because you don't know where the reflection actually happened. So in order to simplify this evaluation, we make an approximation, which is this one, which is valid when this condition is true. So if you look at this one, so the component here that is associated with theta is replaced by all these parameters, which are height of base station. The height of base station doesn't change, so we can assume that we know the height. And the height of mobile station, which can always be estimated by 3D GPS. And then distance and the wavelength, they are all conventional parameters that we are kind of inherently known when we deploy the system. So if we replace this into equation 7, then we no longer need theta. So then we arrive at here. So the first part, we didn't touch it. The second part, we replace the part that is hard to estimate by all the inherent parameters that we can just input them and then get the output signal power. So, and then after this, eventually we want to evaluate this equation in log domain, in decibel. So how can we further simplify this? Is we probably don't want to calculate sine in log domain. So if we want to simplify it, we make another approximation, which is valid when this condition is true. So eventually, this equation is simplified into this really streamlined version. So when you evaluate received signal power, you only need to input transmit signal power, the antenna gains, which are determined once manufactured. So when you are actually given the system, you know the antenna gains and the height of base station and the height of mobile station, and then the distance. So now we need to look at this equation in decibel. We are ready to look at it in decibel now. So we put everything in log domain so that all the parameters are separated. We can look at them separately. One important takeaway from here is that increasing distance by 10 meters, we get 40 dB power loss. Not sure if you remember for the previous path loss, free space path loss, we have this element here that determines that when you move away for 10 meters, there's 20 dB path loss. So free space path loss propagation model is very optimistic. It only considers line of sight. So it tells you that if you move away from the transmitter for 10 meters, you get 20 dB power loss. But 20 dB is considered quite small. Normally, it's more than 20 dB. For ground reflection model that we just see here, when you move away for 10 meters, you get a power loss of 40 dB. So now 40 dB is actually, in reality, is considered really high, but it's more realistic than the free space path loss. So this is a second path loss model. So the first one, free space path loss model, is associated with line of sight transmission, which is the case for satellite communication and it can also be used as reference in normal communication scenarios. And then ground reflection model uses one line of sight and one reflected link, which is a valid model for rural area and also for aeronautical communications, so airplanes. And then the third model is called Hata's urban path loss model, which is named after the Japanese scientists who work out this approximation. So in an urban environment, there are a lot of obstacles. There are a lot of buildings, cars, trees, humans. So when you actually do signal transmission, the signal will experience a lot of reflections. So there's no way that we can model the system in the same analytical way as what we modeled before. So what Hata did was he was driving a car in Tokyo, and he collected a lot of signal data. So the signal data was collected under all of these conditions, right? So and then he approximates the relationship between inputs between the transmit power and the receive power by this unified equation. So for this equation, you are not required to remember very specific parameter here because they probably don't make any sense. They are from collected data. They are from measurements. But it's important to understand why for this equation, all these parameters become more irregular than before, because the environment become more irregular and the environment become more random. So we have to rely on data. I'm not sure if you remember in lesson 1, we talked about the difference between machine learning in computer science and their applications in wireless communications. So in wireless communications, for most of the case, we want to model the environment by mathematical model like this. So these models are more fixed, more deterministic. However, it's not always possible. So Hata's urban path loss model is actually more data-driven. This is an area where machine learning can actually help, because you can see that after he collected all the data, he collected data with some system setup, right? So there is limitation of when you can actually apply this path loss model. The limitations are all here. So with more data from different frequency bands with different system setup, the relationship would become more complicated. That's where machine learning would probably be helpful. So for this equation, there is a correction factor here. So this model is measured in an urban environment, but it doesn't fit all the scenarios. So this correction factor would help you to fit this equation to different scenarios. For example, for small and medium-sized city, the correction factor would give you a more accurate estimate by changing the parameters here. And then for large cities, the correction factor is like this. So once again, these two equations and all the equations for Hata's urban path loss model, you are not required to remember all of them, but it's really important to understand the rationale, how this model is generated, and why we need correction factor, so that we can, it is designed, the correction factor is there for us to fit the model to different scenarios. And then also, so Hatta's rural model can be also corrected, revised into a suburban area scenario and the rural area scenario. So you see all these parameters, they don't really make sense to us because they are from measurements. So this figure here is from measurement that have been done by our research group about 20 years ago. So all the small boxes with crosses, they are data collected by the experiment, and the thick black line is approximation made by our group, and the thin line is Hatta's model. So Hatta's model doesn't always fit. In reality, your mobile phone always feedback signal to the base station. So the base station would always collect a lot of data. So it would dynamically adjust its path loss model. So once again, come back to any questions here? I think I probably spoke a little bit faster this afternoon. So as we said earlier, that we have 3 levels of channel modeling. The 3 methods we just introduced are all on level 1. So propagation path loss. For propagation path loss, we are only investigating the path loss that is induced by distance. So it would change linearly with distance. And we have 3 models or 3 methods here, which fit into different scenarios. The first one is free space path loss, which is associated with line of sight. The second one is ground reflection path loss, which is line of sight and the reflected link. So it's also called two-ray model. This is more suitable for aeronautical and rural area. And then the third method is Hatta's urban path loss model, which is data-driven approximated equation that fits into urban wireless communication environment. So the next level is shadowing. So shadowing is so propagation path loss is a gradual power loss over distance. Shadowing is a more sudden signal blockage due to buildings or hills that is placed between you and the base station. So let's look at shadowing effect. In here, so shadowing effect is caused by buildings or hills that are in the vicinity of the receiver. So it would cause a sudden blockage for the signal reception. So here we say that wireless communication, wireless channels typically experience 3 levels of fading. So as I emphasized many times, the first level is path loss. The second level is shadowing. The third level is fast fading. So now if we want to study shadowing effect, we need to eliminate the influence of the other two. So for path loss, after we know the distance between transmitter and receiver, we know which model we want to invoke, like either free space path loss or Hatta's model or the two-ray model. Then we can calculate this path loss. This path loss is supposed to be compensated for as a transmitter, so you increase the transmit power so that this path loss is compensated. It is compensated as a transmitter. And then we want to study shadowing fading. We also need to eliminate the effect of fast fading. So the method normally is an averaging method, which means you average the received signal power over a distance of some 20 wavelengths. This is an example. This is not a general approach. This is a specific example, but it tells you that if you want to know the power of the third level fading, you need to average the signal power so that you get the average fading level, and then you can compensate this signal power loss as a transmitter. So the only effect that's left in the received signal power's power loss is the shadowing effect. Actually, you only need to if you want to visualize this, you only need to always remember that there are three levels of propagation loss. So first is path loss over distance. Second is blockage. Third is small scale fading, which we will talk about later. So when we want to model one level, when we want to model one effect, we need to eliminate the influence of the others. So shadowing effect is normally modeled by log normal distribution. So from the look of it, equation 19 looks just like a normal distribution. Normal distribution is also Gaussian distribution. So can anyone tell me why it's called log normal distribution? So it's so actually the reason is the x-axis is yes, yeah, well done, yes, that's the exact answer. So the reason is the x-axis is in decibel. So the distribution itself is a Gaussian distribution. So if we look at the PDF here, the x-axis is in decibel. So 0 dB in normal number, it would be 1. So 10 times log 10, 1 equals 0 dB. So 0 dB corresponds to number 1 in normal domain. So when we have the path loss level of, yes, the lecture will be recorded, and I have pre-recorded the session as well. So I have pre-recorded the session before the lecture. That helped me to practice, and also if you want to watch the video before the lecture, you can watch the other pre-recorded version, but basically the content is the same. Okay, so 0 dB corresponds to a fading element in the normal domain of 1. So when we have 1 as the fading factor, it means the signal is not amplified, it is not faded as well. So the signal power remains the same. There's no blockage and there is no amplification. So from this figure, we can see that there's half and half chance that the signal can be amplified, or the signal will be the signal power will be reduced. In communications, normally we wouldn't care so much about the signal amplification because those scenarios are benign. It works to our favor. We need to do something when the signal is blocked. So we need to do something in here. So we call it shadowing effect. We call it a blockage because when the blockage happens, we need to model this effect correctly and then provide signal processing solution to deal with this problem. But it's essentially the reason that it can be either amplified or it can be faded is because different replicas of the original signal, they'll arrive at the destination at the same time, so they can aid constructively or aid destructively. So when the signal power is actually amplified, we're happy about that, but we don't need to do anything extra. We don't need to offer any extra effort. But here, this is more important. This is the reason why we want to model the path loss, and we want to model the shadowing effect. So it was log normal distribution because the x-axis was in decibel. So if we don't want to look at decibel in normal domain, we extended decibel by this. So the variable is of this PDF is in normal domain. So after this transformation, the PDF become like this. So the value 1 here is a boundary. So if the fading is bigger than 1, then the signal is amplified. If the signal is smaller than 1, then the signal is blocked. It's actually still half a half chance, because on the left-hand side we have a high peak, and on the right-hand side we have a long tail. So the area under the curve is the same between the left and the right. So this is a shadowing effect, which is a second level, the sudden blockage. Now we need to look at the third level, which is actually the most difficult part of channel modeling, and we will dedicate a few sessions on this third level, which is fast fading. Fast fading is also called small scale fading. So in communication, sometimes it could be quite confusing because there are different names, but they are referred to the same thing. It's mainly because all of these were developed all the way since 1950s, and over history, a branch of people call it fast fading, another branch of people call it small scale fading, but it's actually the same thing, and the terminology is explainable. So as I told you before, the reason it's called fast fading is because when the signals they add together, for this level of channel modeling, we need to model both the channel power fluctuation and the phase change. So this level of fluctuation, it changed really quickly. So if the destination is moving, so if the car is moving, or if the transmitter is moving, or if the surrounding environment is changing, so if there's a car passing, then the power fluctuation would be really would happen really quickly. So it would fluctuate really rapidly. That's why some people call it fast fading. But it's also right to call it small scale fading, because the previous two levels, the first level is path loss, that is related to distance. The second level is shadowing, that is related to blockage. All these two levels, they are sudden power loss over a large scale, and we need to take into account that power loss by increasing the transmit power as a transmitter, so that the receiver wouldn't feel that it was in kind of a deep fade. But for a small scale fading, it changes really quite quick, and the fluctuation is in small scale, so you wouldn't be able to compensate for this power loss as a transmitter. You have to deal with it as a receiver. You have to model it as a receiver. You have to deal with it as a receiver. So it's also called small scale fading. You don't have to remember the exact meaning, but I hope it makes sense why they are called different names, but they are the same thing. So once again, I will emphasize on these concepts many times over the future lessons. So don't worry if it feels a little bit confusing right now, because we are talking about a lot of concepts today without any means to visualize them. So but try to classify them into different categories. So 3 levels of channel modeling, and why it's classified that way, and why they are called large scale or small scale. So small scale fading is determined by multipass effect. So multipass is you have multiple signals arriving as a receiver, and they are added together. So that's multipass effect. Doppler effect, we will talk about it later in detail with equations and everything. But I already know that Doppler effect, it happens where the signal waveform changes when either the transmitter or the receiver is moving. So when signal waveform is changing, the nature of the signal propagation would change as well. It's like when an ambulance sounding siren is driving towards you, you feel the pitch become higher as the ambulance is approaching you. But actually, from the transmitter's point of view, when it's sounding the siren, the pitch doesn't change. So your feeling as a receiver is the receiver's perspective. So at the end of the day, we normally model everything from the receiver's point of view, and then feed back what we get to the transmitter, so that sometimes transmitter can compensate for example, the signal loss. So if the receiver says we have this signal power which is too low, then this information will be fed back to the transmitter, and transmitter would increase the signal power. Small scale fading is also related to carrier frequency, which is the center frequency of the frequency band that you are using. Bandwidth is ambiguous definition. Here it means the channel bandwidth, which is a coherent bandwidth of the various channel. Symbol rate of the transmitted signal, we often also call it symbol rate of the transmitted signal, or we can call it sampling rate of the transmitted signal, or we just call it the signal bandwidth. They are all interchangeable. Whenever you are not sure about terminology, stick to the terminology used in the slides. So if the, for example, when small scale fading and fast fading, they are shown in the same page in this slide, it means the same thing. The terminology is interchangeable. So whenever you feel you are not sure about the terminology, for example, I said a lot about signal bandwidth, but there is no mentioning of signal bandwidth in the slides. In the slides, it's also said system bandwidth or symbol rate of the transmitted signal. So in exams, you should stick to the wording in these slides. So fast fading, the third level of channel model, is small scale fading, and so I said earlier that for path loss, the first level path loss, and the second level shadowing, we only model the power loss, which is a real value. So we only concern ourselves with how much signal power have lost. And then for fast fading, we need to take into account both the amplitude, which is the power fluctuation, so power loss, and also a phase, because all the signals, they come with different delays, so they have different phases. They add together. It's no longer the same phase as the transmitted signal. I will show you a supporting document in a minute. The important thing from this slide is that from now on, for fast fading, we interpret the fading gain by a complex value. So in reality, in real world, all the signals are real. There are no imaginary signals. Everything's real. So why we can represent signal by complex value? I will show you a bit later in a supporting document. Actually, I think you have already learned a modulation scheme called contracture amplitude modulation. So for that modulation, the signal is represented by complex value. So simply speaking, there's no complex signal in the world. There is only real signal. There's no imaginary signal. But we often represent signal as a complex value because it's easier for us to do simulations. It's easier for us to model it mathematically. So I will show later why it's equivalent. But here we need to remember that for fast fading, it is a complex value, and it has amplitude, which is a power change, and we have a phase, which is the phase change. And then for the complex value here, because we have so many reflections adding together, based on central limit theorem, both the real part and imaginary part will be Gaussian distributed. So they are both they both follow normal distribution. And if we have line of sight, for example, line of sight is a fixed thing, it's a known thing, because there's only one direct link from the transmitter to the receiver. So line of sight is always fixed. So line of sight determines the mean value of the distribution, so the mean of the Gaussian distribution. And then we have a variance of the non-line of sight random elements, and all the variance and the mean, they will add up to normalized power 1. So fluctuation is in small scale, but on average it's 1. So before we finish this lecture, it's very important that I want to show you the course website. Let me see if I can share my screen. Yeah. So someone asked recording, so you can go to Blackboard, and there are recordings here. So every license, there is a pre-recorded version, and then there is a real lecture version. They are of the same content, but it depends which one would be more helpful to you. So this is the course website. You all know where to find it. So I want to mention here that this slide is produced by Rob Monder, who taught this course before me in previous years. So my slides, for my slides, I added some examples based on my research background, and I tried to explain them to you. But today I realized that the software version on my Linux system is different from the version that was used in lab a few years ago. So in my slides, some of the figures can no longer be included. For example, here it's kind of blank. So very important for revisions. You should always refer to this old slide that was produced by Rob Monder here on the website. So it has everything you need to learn. For my version, I will continue to add more examples as we go, but those examples won't be in exams. So it's very important that you look at the right version when you prepare for exams. And notes here. The first one is taken from books written by so researchers from our research group. So it's not a lot. You can see a lot of figures are the same as what we see in slides. So if there's anything you don't understand, this is something you can refer to. And then this material in particular is QAM, contracture amplitude modulation. Under the understanding that you have already learned QAM, which is this one here. So you modulate two part of signals by cosine and sine waveform. And cosine and sine, they are orthogonal to each other. So as a receiver, you can use cosine and sine to separate these two signals, two parts of the signal. So this kind of improve the throughput, because you kind of only use one channel instance, but you are transmitting two data streams. So the reason I mentioned QAM is that QAM is often represented by complex value. In reality, we only have real valued signal, but here we can represent QAM by complex value. And then in the end, from the beginning to the end, we get the same result. So complex value representation help us to do simulations and to model the process of signal transmission and reception. I wouldn't have time today to go through these figures and equations, but all of these contents, I think I'm told that you have learned them before. So the modulation schemes, and especially QAM. So it would be helpful if you have a read on this conjecture amplitude modulation. So yeah, that's actually all for today. Any questions? Sorry, I was under a little bit pressure in the afternoon because I was a little bit slow in the morning, so I probably spoke a little bit fast this afternoon. If you have any questions, send me an email. So, for example, if there's any concept on any page of the slides you are struggling with, then you just send me an email. You don't need to specify why it's confusing to you. You just tell me, for example, what really is shadowing effect. I don't understand shadowing effect. Then I will emphasize on this next time. So yeah, if everyone's happy, that will be all for today. Wish you all a happy weekend. Thank you, guys.